So hello everyone, the official countdown is on, and in just a few days, on April the 1st, humanity returns to the lunar orbit for the first time in over half a century with the launch of Artemis II. It's a massive turning point for science, and today on Geoscientists Voices, we are joined by Dr. Nicolas Randazzo. Nicolas is a member of the NASA Perseverance Science team and a researcher at the University of Alberta in Canada, specializing in planetary geochemistry and meteoritics. Nicolas, thank you for joining me today.
No problem. Thank you for having me.
The honor is all mine. So, Nicolas, Jeremy Hansen, your fellow
Yes.
Canadian, is days away from becoming the first non-American to leave Earth's orbit and head for the moon.
Yeah,
So I know that you've actually met the man. So
I did. Yes.
give us the inside scoop. Like, is he
Yeah.
a rock nerd like us, or does he have that classic Top Gun sort of astronaut energy?
Yeah. So I met Jeremy at the Lunar and Planetary Science Conference in 2023. And what stood out to me is just how naturally he bridges two worlds that often people think are separate. So on one hand, he was composed, highly disciplined. He has that test pilot presence. You can tell he's someone who's trained to operate in extreme environments where precision matters. But what really impressed me was how engaged he was with the actual science itself too. So he wasn't just a representative. He was listening. He would ask questions. He would interact with researchers, and that's really a defining feature of modern astronauts. Like in the Apollo era, the astronauts were trained to do geology, but today they're actually integrated into the scientific process from the beginning. So they're trained to observe, interpret, and make decisions in real time. So he's not like a pilot versus rock nerd. I'd say he's both. And for missions like Artemis, that combination is exactly what you need, because exploration today is as much about scientific judgment as it is about engineering and flight.
Sure. But like looking at the social media from NASA and Artemis mission, and even from the Instagram profiles of the astronauts of these and missions that came before, I think that, and correct me if I'm wrong, that astronauts also have to adapt the third persona, which is science communicator. So do you
Yeah.
think is there a place for such a person as astronaut/science communicator? And do you think that Jeremy is one of such people?
I think he is, and you're right. That's very key, especially with us trying to inspire the next generation, try to get people excited about space science and planetary science. I think it's absolutely key to be a strong science communicator. And from my interaction with Jeremy, he definitely has that. And he's very calm and collected. He seems like he's a very personable guy that I think you can definitely sit down and have a fun conversation with. And I think that's key with science communication.
That's great to hear that. It means that we'll have many more scoops from the mission in really accessible language to common public and to researchers who don't do planetary sciences.
Yeah.
So let's talk about the mission. Artemis II isn't landing. It's doing a massive 10-day loop around the moon and coming straight home. So
Yes.
for me and for someone watching us on YouTube, why is this practice lab actually the most dangerous and critical part of the whole program?
Yeah, so you're right. It does sound simple from the outside. It's just a loop around the moon, but it's actually one of the higher risk, higher value steps for the entire Artemis program. And the key point is that this is humanity's return to deep space. We haven't gone there since the Apollo program, and we've operated almost exclusively in low Earth orbit since the early 70s. And there we have constant communication, we have rapid resupply, like the International Space Station is getting resupplied frequently, and there's always the ability to return to Earth within hours if something ever goes wrong. But Artemis II changes that completely. It's once the crew fully commits to that trajectory, they're days away from Earth. So there's no immediate rescue option. Every system from life support to navigation has to function autonomously and reliably. And then there's the re-entry afterwards. So the Orion capsule it enters Earth's atmosphere at speeds approaching 25,000 miles per hour. And that generates extreme thermal and mechanical stress. And validating that heat shield system is absolutely essential for attempting a landing mission. So this practice lap is really a moment where we can prove that human deep space travel is viable again. And if this works, it unlocks everything that follows, which includes sustained lunar presence and inevitably even Mars missions.
Wow. So hopefully, I mean, it really sounds more complicated than I
Sure.
thought, and probably many people thought as well. So let it be
Yeah.
really safe mission. That's, I think, what most of the people really hope for. It's number
Yeah.
one. Um, so let's talk about now your research, because you've been on the front lines with the Perseverance rover at Jezero Crater, I think, on Mars for
Yep.
5 years now. So why was this ancient river delta, the Jezero Crater,
Yeah.
is basically the ultimate choice to hunt for life? And I mean, as far as I know. And what is one underappreciated discovery, like, for example, that Silver Mountain sample you wrote about in your social, LinkedIn, etc., that
Oh,
we
yeah.
actually should be talking about?
Yeah, so Jezero Crater is very geologically unique. It was selected because it represents one of the best preserved samples of an ancient habitable environment on Mars. And what makes it particularly compelling is that it contains a fossil river delta, which is essentially just a sedimentary system where water once flowed into a standing lake. And on Earth, deltas are incredibly effective at trapping and preserving organic material and fine sediments, work that I actually did during my PhD, and that makes them ideal locations for preserving potential biosignatures if life ever existed. Not sure if you heard about the finding about the leopard spots and poppy seeds that were found in Jezero Crater. That is probably one of the most convincing and best options for life on another planet that we've ever found. We won't know for sure how important it is. It could be abiotically created, but once we bring those samples back to Earth through the Mars sample return mission, we'll be able to actually do really good lab testing. But yeah, it's incredible. Like from an orbital perspective, we can see clear evidence of mineralogical diversity. We see like carbonates and clays, which form the presence of water. And then that can lock in chemical signatures over long periods of time. So Jezero really gives us three things at once. It gives us, for sure, evidence of past water, a sedimentary environment capable of preserving biosignatures, and a really diverse geochemical record. So in that sense, it's not just like a random landing site. It's a carefully chosen natural archive of Mars environmental history.
Wow, it sounds exciting, and I'm
Yeah.
hooked on the
Yeah.
seeds kind of part. And can you just expand a bit? How did you classify that they were seeds? And if you said that they are of not organic, origin, then of what origin if they look like seeds? And finally, when are we going to actually learn for sure its origin? Because you said the return mission of this rover, when is it going to be? I'm really excited
Yeah.
about it.
Yeah, so we have a bunch of instruments on the Mars Perseverance rover, like the Pixel instrument, Sherlock, Mastcam Z, and what a lot of these do is they can take, let's say XRF signatures, so we can look at elemental diversity, we can look at little clues through remote science about what we're actually seeing. So like the leopard spot slash poppy seeds deposit that we saw has vivianite in it, which on Earth, vivianite is often found with life, but there's always a possibility that these samples that we find are abiotic. They might just form through um, natural processes that have nothing to do with life. And this is just really a way of being cautious. In the 90s, we had a meteorite called the Allen Hills 84001 meteorite that looked like there was a little worm on it, and people were really excited. Bill Clinton gave an announcement about it, and then it found out that it wasn't a little worm thing. It was actually just mineral deposit that just looked like a worm. So people kind of jumped the gun. So we have to be very cautious before saying that something is actually evidence of life. So this looks good, but there's only so much that remote science and the Perseverance rover can do. And it's not till it's back on Earth that we actually can do these kind of laboratory techniques with actual humans that we can prove if it's actually biological or not. The issue is actually bringing it back. So the Mars sample return was supposed to come back in the 2030s. Then that got pushed back to the 2040s, and now we don't really know. The return mission ended up being way more expensive than we originally thought. It was supposed to be the whole mission was supposed to be about $5 billion, but now it seems like it might be more around $10 to $11 billion. There was a call out to different companies, SpaceX, etc., to try to bring the costs down. They did bring them down a little bit, I think to like 7 or 8 billion, but still that's too expensive. So we're not fully sure. A lot of this just comes down to government funding and technologies that we are talking about that haven't really been invented yet, that have to be made. So this causes not only a scientific delay, but it also really makes funding a key part. So I hope in our lifetime that those samples will return back to Earth, but I'm not fully sure when that would be.
Yeah, and now let's go back to the moon and to the remote sensing you've been talking about, because
Okay.
NASA's lead scientists for this mission, experts like Cindy Evans and Kelsey Young, they've been training the Artemis II crew to look for color provinces on the lunar far side from their cabin view. So can the human eye really see hidden chemical secrets in the lunar dirt that a robot like Perseverance might just overlook?
Sure. So from a geochemical standpoint, what they're calling color provinces are really just expressions of underlying compositional differences. So on the moon, like variations in color often correspond to differences in mineralogy. So like things like iron content, titanium abundance, or the presence of anorthositic versus basaltic material is something, let's say, was it a lava deposit versus not a lava deposit? And what's fascinating is that the human visual system is extremely good at detecting subtle contrasts like patterns, gradients, little anomalies, especially when you're trained to look for them. So geologists in the field isn't just seeing color, they're interpreting it in terms of context, texture, layering, spatial relationships, and robot instruments can measure composition very precisely, but they do it at discrete points, where humans, on the other hand, integrate information across an entire rock in real time. So that's incredibly powerful for identifying targets that are scientifically interesting, but might not stand out algorithmically, and that's why you need machines. So training astronauts to recognize these features is essential in giving them a form of kind of rapid, intuitive geochemical mapping capability that even during a high-speed flyby, those observations can be used to inform landing site selection, sampling strategies, or kind of broader understanding of lunar evolution. So in that sense, the human eye, when properly trained, is still one of the most versatile geological instruments that we have.
So like AI and all these technologies, they train to look for patterns, and you're now saying that human eye, which is pretty complex, but I mean it's natural organ and not like AI or something that was developed by humans. So
Sure.
it is as good or even better than all these technologies and remote sensors and that actually patterns is something that human eye can recognize as, if not better than AI and all these technologies?
Yeah, the current state of AI, like AI itself, like if you use ChatGPT or anything like that, it's, we treat it like it's intelligent, but it doesn't really know what it's saying or doing, right? So like ChatGPT, for instance, is a language model. So basically, you ask it a question, and it uses statistics to give you an answer. So it'll, let's say, give you a one sentence response. Every word that it gives you it does a series of calculations saying what's the next word that should logically go into the sentence, and then it'll spit out a sentence. So same thing with any AI that we use. It just uses neural networks. We train it. It's useful, but it's still not smart, right? It's just basically advanced pattern recognition. And this could be helpful in scientific studies for sure, but it's not like a human that can actually, let's say, understand the geology, that actually has proper training. It's just basically AI just looking for patterns. So because humans are still smarter than AI, they're still preferred.
You are working with Mars and have been working with Mars for a lot of years.
Yeah.
But people often ask why the moon? And from a geoscientist perspective, how does studying the lunar surface today directly helps us put the first human geologist on Mars in the 2030s? Or how does it help in any way with your work, if you work solely on Mars and not the moon?
Yeah, so lunar exploration plays a critical role in preparing for Mars. So not just from an engineering standpoint, but also from a geoscientist perspective as well. So the moon gives us a nearby environment. It still takes, I think, about 8 to 10 months to go to Mars, whereas like 4 days to go to the moon. It's a nearby environment where we can test how humans operate as field geologists in another planetary environment. And that includes how astronauts observe terrain, making sample decisions, or even interpreting geologic features in real time. And it allows us to refine the integration between human and robotic systems. So this is like how astronauts work with these instruments, how data is collected and transmitted, and how decisions are made in environments with communication delays. So from a scientific perspective, the moon helps us practice reading planetary surfaces, and that's understanding impact processes, regolith development, the evolution of crustal materials, and those same skills can then translate directly to Mars, even though the environments are different. So in many ways, the moon is a proving ground, not just for the technology, but for how we actually do science on another planet. And that's essential if we want to be effective when we eventually do get humans to Mars, whenever that would be.
I have heard, I'm not a planetary scientist, so I have no idea if it's true, that the
Okay.
moon can be sort of like a launching pad for rockets that might go to Mars because of less gravitation than on Earth, and meaning that we won't need that much effort to actually get it off the planet compared to Earth. I'm not sure if it's like a theory or myth that has to be busted, but what do you think about it?
Yeah, so there's a couple things here. So I think you're referring to like a gravitational slingshot, where basically you can orbit around a planetary body, and this is also how we can get into do eventual deep space missions too, or how we, I guess, do deep space missions. Basically, you can orbit around a planetary body, let's say like the moon, and then have its gravity kind of assist you. And so if you can, let's say the moon is here and you're coming, you can orbit the moon a few times and then kind of use that momentum gain to slingshot you towards a new direction. So that's one thing. And then there's also talks about the Lunar Gateway, which will eventually be built on the moon, which is essentially will be like a hub for people to actually eventually go from the moon to other locations. So it would be like an outside of the Earth, low atmospheric resistance eventually like spaceport that humans can eventually go, but that's years and decades away. But that's kind of the eventual idea as well.
So what you're talking about, the lunar port, I think I saw it in the movie called Ad Astra with
Okay, yeah,
Brad
with
Pitt.
Brad Pitt.
What I remembered from this port, like the image that stuck in my mind, is that they had Subway sandwich stand there. So it's like the corporations are there, and uh, so just in broadly speaking, how far away are we from it?
That's hard to tell. I would hope that we will both see this before we retire, but obviously we don't, these things take a long time. Even the James Webb Space Telescope, I think, took 20 plus years before that got off the ground. So yeah, I don't know. It would be great. It might be more realistic to assume that, yeah, it will be your kids or grandkids that would see this, but it would be wonderful if it happens sooner rather than later. But yeah, I have no idea. I'm not sure.
Yeah, so let's see.
Yeah.
But now let's talk about really serious stuff, coffee. Nicholas, you're known coffee scientist in your spare time, as I know, as I read. So
Yeah.
Jeremy, who is like the astronaut, Canadian astronaut, who will fly to the moon, is about to spend 10 days in the Orion capsule, the size of a camper van, drinking
Yep.
only instant coffee from a bag. So, I mean, just crazy. As an expert, how
Yeah.
on earth does he survive that coffee crisis?
Well, it's hard to just live off of instant coffee like that. I think he's going to have to. Fortunately, that mission will be short, so he won't have to suffer for too long. But it's actually interesting that you bring up coffee, because space coffee or having coffee in space is a great example of how even like simple everyday things can become more complex if you're trying to provide them to astronauts, but also to the kind of the psychological aspect to even being in the International Space Station and having to be without things that we take for granted on Earth a lot. But even like having coffee on the Artemis II, it causes a lot of engineering problems because you're in microgravity right now. So like on Earth, coffee relies on gravity, right? The water flows through the grounds. There's volatile compounds that are released. The aroma plays a role in how we experience it. But when you're in space in microgravity, you lose that process, right? So like liquids behave differently. Maybe you've seen videos of like Chris Hadfield or like some of these astronauts in the International Space Station where water doesn't flow, it just floats as bubbles. Convection processes are altered and you can't even use a standard coffee maker like you said. So they have to rely on this pre-packaged or reconstituted coffee, which lacks a lot of that complexity and aroma we associate with a good cup of coffee. So there's the physiological aspect with just like the fluids and microgravity that dulls your senses of taste and smell. So yeah, it's a small detail, but it really reflects a broader challenge for us. And solving problems like this could be eventually key for long-term missions where again we have to go without, and things behave very differently in space. A lot of inventions were created because of space exploration, like even like developments in camera technology or like in weatherproofing. Like there's a lot of different things that now we take for granted and we experience every day that once upon a time didn't exist. And the only reason why some of these things exist is because a need develops. And in this case, we're talking about coffee in space, but perhaps that can create a new technique that can eventually be brought to Earth and something that can become commonplace in like 70 years could be developed because of something that Jeremy wanted while on the Artemis II mission. So it's interesting. It's actually very very cool from a historical perspective.
So, Nicholas, you are a meteorite expert, and Orion, a capsule with the astronauts we already talked about, is going to hit the atmosphere, as you said, at the speed of 25,000 miles per hour, which is just
Yeah.
crazy. I can't imagine that.
Yeah.
When and it will happen when they will be coming back to Earth. So, simple question, but important one. The first one is it dangerous? And the second one, how does that compare to the natural space rocks you track across the Canadian wilderness?
Actually, while at the University of Alberta, worked on what's known as the Desert Fireball Network, where we're collaborating with colleagues in Australia. And they have something similar at Western University as well in Canada. But basically, it's just a system of cameras that just always monitor the night sky. And when a meteorite falls, if 3 or more cameras that are located throughout the province locate it, we can triangulate and find the meteorite, and then we can do studies and things like that. And the sooner you get a meteorite, there's less contamination. But to answer your question, from a physics perspective, both meteorites and the Orion capsule, as well as a space shuttle or anything else, are experiencing very similar fundamental processes with atmospheric entry, and that's just extreme rapid compression of air and the formation of very high temperature plasma envelope that goes around an object because it's going at such high speeds, and there's such resistance from Earth's atmosphere that actually the friction causes the air to actually turn to plasma, which is pretty insane and lets you know how high those temperatures are. So for meteorites, the process is chaotic, right? Their mineralogical composition and structure can determine how, if they fragment at all, if they ablate, and whether any material survive to the surface, right? A lot of times these meteorites will just burn up in the surface and they won't actually fall onto the Earth, but many times they do as well. And again, that's just, is it made of metal versus is it made of rock? Did it have any fragments in it, etc.? And even when the meteorites do make it to Earth and we find the meteor, you can see that they're very smooth surfaces. It looks like almost like desert varnish, or you'll have little scoops that are actually pulled out of them, that basically where the rock was gradually being vaporized as it fell. But yeah, it's interesting. The Orion, on the other hand, it's a more controlled system. Its shape, its trajectory, and its heat shield are all engineered to manage those same physical processes. And there's a thermal protection system which is designed to kind of absorb and dissipate heat in a predictable way. So this allows the spacecraft to survive conditions that would normally destroy, let's say, natural material. So the key difference is, because we know these processes and we have more control and the design and everything, it's a controlled re-entry versus the randomness of a meteorite. So, meteorite survives by chance, whereas Orion survives by design. And as a geologist, I find both really fascinating. But there's something uniquely compelling, I think, about our understanding of planetary entry processes and translating them into a system that can safely return humans from deep space.
So with this Orion new technology, do you think it will also be beneficial for the comfort of the humans returning to the Earth?
Yeah, I'm sure the Orion capsule will be more comfortable than what was experienced during the Apollo days. But at the end of the day, it's still tight quarters. And this is actually part of the psychological training of an astronaut, is to test for things like claustrophobia. At the end of the day, these missions, it's not like a private jet where we're trying to make everybody as comfortable as possible. We're trying to get as much important equipment and humans to the moon or Mars or the International Space Station. But the more material we bring, the bigger the capsule will be, the heavier it might be, and then that takes fuel considerations that could potentially create further risks, because now something is wider or heavier than what's optimal. So it's it's really the main focus should be on the science and what's kind of the minimal amount of comfort that these astronauts can take to ensure the maximum likelihood for mission success.
The final and probably most important question that I want to ask you, I want to ask you to answer from the position of lecturer in the University of Alberta, where you give lectures, is that with this Artemis era officially kicking off in a few days, hopefully, what is your message to students who want to bridge the gap between Earth-based geology and exploring other worlds?
Yeah, great question. So what's exciting now is that the boundary between Earth science and planetary science is essentially disappearing. So the principles that we use to study sedimentary systems, like this is what got me on the Perseverance rover mission to begin with, things like facies analysis or just geochemical analysis or studying the planetary evolution of Earth, they're now directly applicable to our understanding of Moon, Mars, and beyond. So for students, the most valuable thing you can do is just build a strong foundation in core geoscience, and that's understanding rocks, processes, and systems that at a very fundamental level. But at the same time, develop complementary skills like data analysis, remote sensing, working with large data sets. These are things that undergrads and graduate students studying Earth do all the time. And those exact same skills are directly being used by members of the Perseverance or Curiosity missions. Modern planetary science itself is incredibly interdisciplinary. And basically you're combining field-based intuition, like we talked about earlier, with computational methods and spacecraft data. And it also really emphasized curiosity. Be willing to move between disciplines or ask broader questions about how planets form and evolve and potentially support life. Right? This is some of the stuff that I talk about in my Geology of the Solar System class at the University of Alberta. And it's important because the next generation of exploration isn't just about reaching new worlds, it's about understanding the planets themselves or the planetary bodies, even if it's an asteroid or something, but understanding them really at the same depth and detail that we understand Earth. So I think that's the best advice I could give right now for students.
Nicolas, thank you so much for really great advice and
Thank you.
The curiosity and all the things that you told about. I think they are really important, and many people mention that. And I really pray that more and more students will get curious and will stay hungry and go out of the box to invest their time and abilities in the further space exploration. And I also thank you for your time and for sharing your insights on the geochemical synergy between Mars and the Artemis program. It's really been a pleasure, Nicolas.
It's been a pleasure for me as well. Thank you so much.
Thank you so much. And to our viewers, thank you for joining us. Be sure to subscribe to Geoscientists Voices on YouTube and on all podcast platforms for more expert perspectives on planetary science, like this, for example. And we'll see you in the next episode. And remember, every mission like Artemis reminds us that we aren't just observing the universe, we are finally becoming a part of it.